Hey everybody, my name is Jeff Varner, and on behalf of my co-workers, so folks from my lab at Cornell and our collaborators at the University of Vermont Medical Center, I'm here to present a package that we developed for building biochemical systems theory models, or BST models, of coagulation dynamics. So the BST model kit package is a lightweight package that transforms a model specification file where we describe the structure of the model into a set of BST differential equations. We're focused on modeling metabolic or signal transduction networks, and it solves these equations using differential equations.jl. Okay, so what is a BST model? So if we focus here on this little toy network here, so what we're modeling is the concentration dynamics of the different chemical species in these types of pathways. So for example, if we focus here on metabolite B, let's say, so traditionally we would build a model that looks something like this. We'd write a differential equation around the concentration of B. We would have a set of terms that produced B, and then we would have a set of terms that consumed B, where these R's here, these are the kinetic expressions. So let's say Michaelis-Menten in the case of enzyme catalyzed reactions, or Hill functions, or whatever it happens to be. So biochemical systems theories models, which were developed originally by Savageau starting back in the late 60s when he was a graduate student at Stanford and have progressed through the years, these take a slightly different perspective. So these are power law representations of the net production rate or the net consumption rate. And so you can interconvert between these two representations by essentially log expanding or Taylor expanding the log of these net rate of input or net rate of output. So BST models, there's different representations, and what we're going to talk about today is something called the S-system representation, which is this net power law type representation. They have a really nice mathematical structure. So you have essentially a lumped rate constant that describes the net rate of production of component I, and then a lumped rate constant that describes the net rate of consumption of component I, and then these reaction orders G and H are your nonlinearity in the system. Okay, so how do we go from that equation form to actually building one of these models? So we have different types of model specification formats. So what I show here is just an example of a flat file format. We also take JSON, TOML, and we're working on SBML. But the big idea here is that I have some sort of model representation that's just a file. I load that, I pass that path parameter into a build method, and we get back this BST model type. And that BST model type contains everything that we need in order to simulate the model, in particular the stoichiometric array, so the G, so the reaction order array, and then our rate constant array, in addition to some other initial conditions and so forth. Okay, so the package exports this BST model type. And then it also exports a number of different functions for working with those. For example, evaluate will solve the model, steady state will solve the dynamics of the model. So all it's doing is taking the model type, pulling the data out, making an ODE problem, and calling into differential equations.jl. Steady state works in a similar way. And then we've also did this for we've taken the model type, a performance function, and we'll call into global sensitivity. In this case, this is the Morris method. We've also implemented Sobel here. Okay, so this is how we create the model. So I wanted to spend a few minutes here talking about the case study that inspired this, and that's looking at maternal mortality rates. So this was an article actually in March from the Wall Street Journal that talked about how maternal mortality in the US has hit the highest level since 1965, and there are pretty stark racial disparities there. So if we dig down in that data a little bit and just sort of summarize, So in 2018, there were on order 17 maternal deaths per 100,000 live births. And in 2021, there's about 33. Okay, so we've seen on order a doubling of the deaths per 100,000 live births. And we've known for a long time that coagulation, the proteome, both the coagulation proteome and the fibrinolytic proteome are significantly altered in pregnancy and often leading to hypercoagulable states, so meaning increased clotting potential. And so this is seen here, pregnant and postpartum women have about a 4 to 5 times higher risk of developing clots compared to non-pregnant women. And between 2017 and 2019, if you just look at this thrombotic embolisms, that's about 8.7% of pregnancy-related deaths have to do with clotting. The other interesting bit here, though, is that hemorrhage has caused about, on order 14% of the deaths can be associated with hemorrhage, which is not a hypercoagulable state, it's a hypocoagulable state. So we have coagulation malfunctions both. They clot too much, or they don't clot enough. And so we have been part of a clinical trial going on at the University of Vermont where we're trying to study this set of biochemical interactions. So in particular, we're looking at the formation of clot here, or fibrin, and how it gets managed. But what I'm going to talk to you today about is actually a little bit upstream of that, and that's how clots get formed, how it gets initiated, and in particular, how we activate this key protease here called thrombin. So this is the output of the coagulation cascade. This has been modeled by many folks, including us and the Vermont group. And these models tend to be pretty large, so they're on order 50 to 100 ODEs. They have a lot of kinetic parameters. So there's a lot of uncertainty associated with this. So we decided to take a different track here. Instead of building these everything in the kitchen sink models, we wanted a low-order biochemical systems theory model, which is only 17 differential equations and only a handful of parameters that we don't know, as a low-order alternative to these traditional kinetic models. And so the question is, okay, well, does it describe the data that we see? Because we're giving up an awful lot in terms of the biological description. So the first thing that we did here is we just stepped back and we just looked at the data. And so our data set here is a population of 37 patients where we have longitudinal data going from before they were pregnant, first trimester, second trimester, third trimester, delivery, so literally right after they delivered, and then 6 months afterwards. And so we have, for each one of these visits, we have 32 clinical features that we are monitoring, so coagulation of fibrinolytic proteome and functional data. So in other words, what we're going to talk about today is something called thrombin generation assays, which is how well do these pregnant patients generate thrombin. And so if you just look at the data itself, we did some synthetic data analysis here as well as looking at the actual patient distributions. So if you look at this plot here, the gray circles that look kind of the smush in the background, this is all of our synthetic population. The open blue circles are our synthetic patient population that we constructed just by computing the covariance and the mean from the data itself, and then the filled-in circles are visit 1, our actual visit 1 patients. Okay, so what we can see is if you just compare V1 to V6, that as the patient moves through the course of pregnancy, they move from the lower left to the upper right, and so that's interesting because this is factor 10 levels. So factor 10 is a precursor to thrombin activation on the horizontal axis, and on this axis is the maximum clot firmness, so how well they clot. So that's interesting. But in addition to looking at the population, we can dig down to individual folks here. I'm just going to focus here on, for example, this panel. So on the horizontal axis, we have time, and on the vertical axis, we have activated thrombin. So this is what a typical thrombin generation profile looks like. So the solid blue here, this would be the the actual subject 1 thrombin curve for visit 1, and the orange would be the thrombin curve for the visit 6. And this region around it, this is a synthetic population of patients that we created by sampling in a local region around subject 1. We did this just by using our distribution and then using a kernel method to essentially calculate similarity and throw points away that aren't similar. Okay, so if you just take a look at this, this is subject 1, this is 42, this is 24, and this is all, well, for 12 of the data points. You can see, you can see that, for example, the peak in the orange is higher than the peak in the blue, so you become more coagulable as you become pregnant, and the area under the curve is larger. We can then, of course, interrogate any one of these patients in our 37 real patients or any one of the synthetic patients, and that's shown here in this panel where we did more sensitivity. And so this is V1 and V6. So V1 is basal, not pregnant. V6 is third trimester. And we can figure out what parameters are important, not only globally to the overall response, but then we can start to compare V1 to V6 at a patient, individual patient level. So we can, for example, figure out subject 1, what's making subject 1 work versus subject 42, because subject 42 has a particular abnormality which will give them about a 15-fold increase in their likely to miscarry, PCOS. Okay, so what did I talk about today? So we developed this BST model package to study coagulation dynamics. So BSTModelKit.jl is a lightweight package that sort of rides above differential equations JL. And it's used to simulate these sort of low-order coagulation models. And we interrogated those models for individual patients in basal as well as third trimester. So I want to thank our funding sources. This work was supported by the NIH. This is the trial here, which is ongoing. We're just finishing up our enrollment. And then this is a R01 that was precursor R01 to the trial. Okay, and I'd be happy to take any questions. Thank you. Chris.
Yeah, so I'm kind of curious that you're targeting differential.jl, but then you said that you're trying to look into doing the SBML reading, right? But is there a reason why you haven't been using the quantum toolkit interface, especially with the SBML toolkit reader?
No actual reason. It's just I didn't do it. So it's and that's why I'm interested in what was talked about in the session. I talked to some folks, and so that may be a next step for us. Because I'm just going to say, maintaining, for example, with the flat file parsing and the format, maintaining that parser, huge headache, right? And it's kind of brittle. So to be able to plug into more standardized tools, I think would be a great step for the package.
Was there a discoverability issue? Like, did you not know about it before being?
Yeah, that was an issue. I mean, this is a fairly, and it was also, I had to get this done before my NIH, investigators meeting, so I just did what I knew how to do. But now that it works and we've shown some proof of concept that it's okay, there are a number of different directions that we're going to go. And one is to make it more usable to other folks, because you can use these types of models in metabolic applications too, and they're quite powerful there. Thank you.